Welcome to the fourth video in the Extreme Network series exploring network automation and workflows. While not mandatory, it is highly recommended to watch the first three workflow videos prior to continuing with this video, as many foundational concepts are discussed. Nonetheless, this video will examine advanced concepts that use Python code to embed external calls using application programming interfaces, or APIs, within a site engine workflow. Additionally, this video will explore API development tools, schemas, and best practices. Before continuing with this video, the workflow used during this exercise can be downloaded from the Extreme Networks GitHub site and imported into Site Engine to allow for closer examination of the API usage. Simply follow this link in a web browser to download the workflow bundle. So first of all, what can be expected in this video? What is the end goal of this exercise? Well, at a basic level, the goal is to examine a pre-built ExtremeCloud IQ Site Engine workflow that extracts all active clients, those that are currently online, from both the Site Engine and ExtremeCloud IQ systems, and then stores this combined collection of clients, along with their identity details, into a cloud-based database system. However, at a deeper level, the key educational takeaway is the integration of three separate APIs within a single workflow to complete this automation task. First, usage of the API commonly referred to as the northbound interface, or NBI for short, is explored. The northbound interface is the native API specifically for ExtremeCloud IQ Site Engine, and in this example, delivers a list of all active clients, or end systems, processed by Site Engine. Second, the implementation of the native ExtremeCloud IQ RESTful, or REST API, is examined. In this workflow, the XIQ REST API performs a similar task and delivers a list of all active clients, but just those that are processed by XIQ. And while the XIQ REST API is completely different than the Site Engine's northbound interface, Python programming is the integration glue that allows these two distinct interfaces to be combined into a single tool, and in this example, produce the same required results, a list of active clients and their associated identity fields. And finally, this combined collection of active clients is then stored in a commercially available cloud-based database via its own REST API. So those are the three APIs that are embedded into this workflow example. And as this exercise continues, the focus will remain on techniques to explore an API's capabilities, determine the necessary API calls for a particular project, and then with the help of Python, implement those API calls into a workflow. So let's begin by exploring the northbound interface API that is presented by the Site Engine. Under the covers, this interface is really a GraphQL API, which is the same API used by many of the world's largest commercial and social media internet sites. To begin exploring an API, the API schema must be examined. The schema for a particular API defines the available data resources presented by the service, as well as the operations and methods to successfully interact with those resources. The raw schema for the northbound interface is available within the Site Engine Server Utilities section of the administration screen and is a text-based representation of all of the resources that the Site Engine makes available via this API. For example, the northbound interface provides access to managed devices, configuration archives, and client end systems collected by the Network Access Control System. And all of these items are defined within the schema. However, browsing the text-based schema provides no joy, and it's not really an efficient technique to explore the potential capabilities that an API offers. Instead, APIs will generally have a schema explorer that allows the developer a streamlined approach to both examine the API schema and manually perform queries. In the case of the Site Engine, the NBI Explorer is used to browse the northbound interface schema and simultaneously experiment with real API calls against the underlying system. For example, building out a simple query against the northbound interface to list all end systems by MAC address takes only a few seconds to create with the help of autocomplete functionality. And as it so happens to be, this is actually the first API query necessary in the workflow example to build a list of all end system clients and their identity fields. However, it is only a list of MAC addresses. There is no way to tell if a given client is active, and furthermore, there is no associated client details such as IP address, username, or hostname. So let's browse the northbound interface schema and see if there's another query that would provide those additional required fields. To do this, let's use the Documentation Explorer that is built into the NBI Explorer to provide a hierarchical view of the entire schema. Beginning at the top of the schema, note that there are two pathways to follow: query and mutation. The mutation branch provides the list of calls that update or mutate objects. However, for this exercise, select the query hyperlink to drill into the vast collection of queries available from the northbound interface. As the goal is to explore client-related data, select the Access Control section. Within Access Control are all of the available queries related to the Network Access Control system, and many of these items are directly tied to end system data. Note that right at the top of the list is the All End System MACs utilized in the first query. Browsing through the remaining access control queries, one option stands out as potentially useful. The end system by MAC seems to have potential to provide greater end system details and requires only a single parameter be passed to it, that of a MAC address. Exploring further, drilling into the WS end system result link provides all the potential results or fields that can be returned by the end system by MAC query. Furthermore, drilling into the end system DTO, or data transfer object, provides a complete list of the end system objects that are available. Browsing through this list, the required fields for the workflow appear to be available. In particular, hostname, IP address, MAC address, username, and state. While not obvious, the state field provides the real-time state of the individual client session. So now that the schema has provided the details to query the northbound interface, let's try the query within the NBI Explorer. First, let's copy one of the MAC addresses from the earlier query and begin building our query while referencing the hierarchical schema as needed. Remember, when building the queries, the autocomplete function of the Explorer will help provide the list of available objects and parameters available at each level and ensure they are entered with the correct spelling and case. Also, the Prettify button applies proper indenting to the query as it is being built and helps clarify any errors that were accidentally entered. When the query is complete, hit the play button to examine the results. There is one last step in building this query. The success variable needs to be added to determine if the query was successful. After running the query again, note that the value of success is a Boolean and in this case is set to true. This additional item returned by the northbound interface can be referenced by Python code and provide a decision point as to whether the results of the query are worth processing. At this point, these two NBI queries can be copied and pasted into a Python script to be embedded into a workflow. If a past query needs to be examined again, the History button in the NBI Explorer provides access to all recent queries. Returning to the workflow's development interface, let's edit the Python script associated to the Query Active Clients in Site Engine via NBI activity. Note the first NBI query that returns a list of all MAC addresses within the access control system is set to the Python variable NBI query. This query is then executed via the emc_mbi.query function, and the results are stored in the Python query results variable. As the results are in a nested dictionary, the Python list of MAC addresses are then extracted and assigned to the all_nsystem_macs variable. Scrolling down through the Python script, the second MBI query has been set to the MBI query variable. Note how the actual MAC address has been replaced with the $nextMAC string. Remember, this is the query that takes a single MAC address as a parameter and returns the key identity values as the query results. Next, a Python list called Site Engine Clients is initialized. This list will be the storage vessel for all individual clients as they are processed. Scrolling further into the Python script, note the for loop that iterates through each MAC address obtained from the first NBI query. As each MAC address is processed, the second NBI query is updated by replacing the next MAC address with the $nextMAC string. The query is then executed and the results are processed. First, the success variable is extracted and is set to true. The remaining results of the query are processed. Basically, the hostname, IP address, MAC address, username, and state variables are all processed, verified, and then stored as a dictionary into the Python Site Engine Clients list. Finally, the Site Engine list is converted to a JSON format, and then using the emcResults.put function, stored as a workflow variable for later processing by different activities within the workflow. The active clients associated with access control on the Site Engine have now been processed and prepared. Next, active clients within the ExtremeCloud IQ system must be gathered. In a similar process to using the MBI Explorer, the Swagger web interface can be used to explore the XIQ REST API. However, before the Swagger interface can be used, ExtremeCloud IQ API authentication credentials must be verified or created. To do this, log into ExtremeCloud IQ and select the Global Settings option and then Account Management. Either isolate an existing local administrator, not an external administrator, or create a new one. Note, XIQ API authentication requires a local administrator account. To open the Swagger interface, enter the XIQ-Swagger URL below. This Swagger interface allows full exploration of the XIQ API, but first, authentication is required. To authenticate the Swagger interface to XIQ, expand the /login entry. Note all of the details presented by Swagger regarding this login call to the XIQ REST API. For instance, the format to apply login credentials, the resulting web code, and example results are all displayed. To experiment with the Swagger interface, select the Try It Out button and apply the local administrator credentials into the supplied fields. Once the credentials are entered, select the Execute button and examine the response from the XIQ REST API. Note that the results for the login provided an access token. Copy this token into the buffer, and then scroll to the top of the Swagger interface and select the Authorize button, and when prompted, paste the access token from the copy buffer and submit the authorization credential. If successful, the authorized icon displays a closed lock. Now that the Swagger interface is authorized against XIQ, other REST API calls can be explored. Browsing through the calls, there are sections for authorization, account information, administrative users, devices, clients, and locations. As the goal of the workflow is to extract the active clients from XIQ, let's examine the Clients section. Note that there are two GET options which refer to REST API queries, and the /client/active has a description of list active clients. By expanding the Active Client section, further API details are displayed, such as the optional filters available to enhance the query. Additionally, the page number and page size parameters provide controls on the amount of individual clients returned by a single API query. The page size parameter sets the total number of clients returned on each page, and the page number parameter selects a specific page to return. Later in this exercise, the Python code will be examined to show the specific usage of page number and page size within the API query. As before, these REST API calls can be executed from Swagger against the XIQ API. Simply select the Try It Out button, keep the parameters at the default values, and then select the Execute button. The XIQ system then processes the query and returns the results to Swagger in a common JSON format. And note the specific results returned by ExtremeCloud IQ. The host name, MAC address, IP address, and username fields required by the premise of the workflow are all available. Returning to the Site Engine interface, the goal is to embed the REST API query for the XIQ active clients into the workflow. However, when using the Swagger interface, the first step was to authenticate to XIQ with a valid local administrator username and password. This is still the case when using the XIQ API from a workflow. As a best security practice, username and password credentials should not be hard-coded into a script. To avoid this security issue, the Site Engine's local credential facility within the administration interface can be used to provide secure storage and easy credential retrieval via an API call to the northbound interface. To store an API username and password securely within the Site Engine, an administrative profile must be created. First, in the CLI Credentials tab of the administration screen, select the Add button. Enter a description for the credentials, enter the API username, set the type to SSH, and then enter the API password in the Login Password field. To allow this API credential to be referenced by an MBI call, it must be associated to a profile. In the case of this example, the workflow will search for a profile named XIQ_API to locate the API credentials. Add a new profile with the name of XIQ_API, keep all the default SNMP values, and then set the CLI credential field to the previously created value of XIQ_API_user. With the XIQ API credentials now stored, let's return to the workflow and examine the Query Active XIQ Clients via API activity. Scrolling to the start of the Python script, note that the XIQ API profile is set to the variable Site Engine Profile and then passed to the Python function getCredentials. This is the function that queries and returns the credentials for a requested Site Engine profile. So let's take a closer look at the getCredentials function. As can be seen, this function takes the Site Engine profile as a parameter, inserts that parameter into a northbound interface query, executes the query, parses the query results with a regular expression, and if a set of credentials is found, returns those credentials to the main program. What's extremely useful about this particular function is that it can be embedded into any workflow where API credentials have been stored and need to be securely retrieved. The heavy lifting has already been built. Returning to the main body of the script, after the credentials are processed, the API username and password are passed to the getAuthorizationToken function. As performed manually within the Swagger interface, authorization of the API credentials must be validated against ExtremeCloud IQ, and if successful, a bearer token is returned. Scrolling to the getAuthorizationToken function, let's examine the details a little closer. As can be seen at the top of the script, the Python request library has already been imported and is available for use. The requests library is the most common library used in Python code to formulate HTTP requests and is used for all REST API calls within this example workflow. Additionally, a global URL variable is set for the Python script, pointing to the base URL used for all ExtremeCloud IQ API requests. Setting a global variable for the base URL of an API is a best practice as it helps to improve the readability of the Python code. Within the getAuthorizationToken function itself, the API username and password are received as parameters, and then some HTTP headers are built to describe the format of the data being passed to XIQ. In this case, the credentials are placed into a JSON payload, matching the header's definition, and then combined with the /login URL as defined by the XIQ API schema. This collection of API details is then sent to XIQ via the post function within the Python request module and results in an authorization or bearer token returned by XIQ. Returning to the main body of the script, the bearer token is received from the getAuthorizationToken function and is stored in the bearer token variable. This token is the required form of authentication that must be included in all subsequent API queries against XIQ. Continuing with the Python script, the getActiveClient's Python function is called and is passed the bearer token as a parameter. The purpose of this function is to request from XIQ all currently active clients. Looking deeper into the getActiveClient's function, once again a REST API call to ExtremeCloud IQ is being prepared. Again, the HTTP headers are built up first, and in this example, the request is for the results to be returned in JSON format, and the bearer token is provided for authorization. And as there may be many pages of active client data returned, a Python while loop contains the API GET request. And based on the configured parameters, the GET request is issued once for each page of client data with no more than 10 active clients per page. As the while loop processes, the active clients are extracted from the API results and appended to the client list. Once all of the pages have been requested, the client list is returned to the main program. Returning to the main body of the script, the list of ExtremeCloud IQ active clients is received from the getActiveClients function and then processed to format the fields in a normalized manner. Once the normalization process is complete, the XIQ clients list is converted to JSON format and stored in a global workflow variable for later use. From a best practice perspective, Python functions should be used to contain and isolate the programmatic details of an API call, as this removes the complexity from the main body of the program and improves readability. Furthermore, Python functions support code reusability within the program itself and between different workflows and projects. The Store All Active Clients in Cloud database is the final activity in this example workflow and has the role of writing the list of active clients extracted from the Site Engine in ExtremeCloud IQ into a third-party cloud database. The cloud database used in this example is called RESTDB.io, and in the same fashion as ExtremeCloud IQ, provides a REST API to support all necessary database transactions such as queries, adds, and deletes. So while RESTDB.io is a third-party cloud service, it is programmatically handled in the same manner as ExtremeCloud IQ, as both services support a REST API. And this can be seen within the Store All Active Clients in Cloud database activity. As before, the Python request library is imported, a global variable is set for the RESTDB.io base URL, and Python functions are created to handle the complexity of the REST API calls. One minor difference of note is with regards to the usage of HTTP headers. Each REST API may support or require the usage of different headers. For example, the ExtremeCloud IQ REST API uses the authorization header to pass its bearer token, while the RESTDB.io API accepts its authorization token with the X-API key header. Keep in mind, the best practice when working with any API, especially a third-party API, is to fully review the documentation and in particular, searching for examples of recommended API usage. A second difference with the RESTDB.io API is with regards to the creation of the authorization token. Rather than automatically generating the token via a REST API call, RESTDB.io tokens are created manually by the database administrator. However, much like username and password credentials, these manually generated tokens can securely be stored in a Site Engine profile. Simply add the token into the password field of the CLI credential that is associated to the profile. In this particular example, the RESTDB.io authorization token is stored in the RESTDB_API profile and is retrieved using the same Python getCredentials function that was previously used to retrieve the ExtremeCloud IQ credentials. With the RESTDB.io REST API specifics now covered, let's review the main body of the script to understand the actions that are taken. Once the credentials are verified, the getRows function is called against the RESTDB.io database, and all existing rows in the table are returned. As these rows contain the client data from the previous execution of the workflow, they must be deleted. Stepping through the list of rows, the ID for each row is extracted and then passed to the deleteRow function. When complete, the database table is empty. Next, the script loads the global workflow variable that is storing the Site Engine active clients and converts the JSON string back into a Python list. The list is then iterated with each client added to the RESTDB.io database with the addRow function. Once complete, the process is repeated for the list of active clients from the ExtremeCloud IQ service. Before running this workflow, the RESTDB.io database must first be created with a single table that contains 5 text fields named MAC address, hostname, username, IP address, and source. Once the table is created, the base URL for this RESTDB.io instance can be copied into the URL variable at the top of the Store All Active Clients in Cloud Database Python script. All that's left now is to manually run the Store Active Clients in Cloud Database workflow and examine the results. As an individual workflow activity is running, it is colored blue, and when successfully completed, turns green. Once the workflow has completed, the results for each activity can be examined. For example, the show output for the Store All Active Clients in Cloud Database activity show each database transaction that was taken. And finally, by displaying the web interface table view for RESTDB.io, the combined list of active clients from both ExtremeCloud IQ and Site Engine are readily visible. So this concludes the 4th and final video in the Extreme Network series exploring network automation and workflows. Thank you for watching.